Hello students, thanks for joining me. So in our last couple of lessons we've been talking about trigonometric identities, and we've been using what I would call the basic or fundamental 8 identities, the ones that are most likely to be used in calculus. But we do have a couple of days that we can spend looking at some of the other identities that I would normally teach a class in a regular school year. So today we're going to look at what we call sum and difference identities. And I'm just going to keep this really brief and not go into as much detail as I typically would. Now, just to keep my notes numbering system on track, we're going to call this one 44.5. Your last notes was 44, I think, and I have another one planned that's 45, so let's just put this one in the middle. Okay, so I have a question. What if you wanted to find the exact answer for sine of 75 degrees? Do we have a way to do it? Well, notice that 75 degrees is the same thing as 30 plus 45. And we know how to find the exact value of sine of 30 degrees. We would draw a reference triangle. We end up with 1/2. And we know how to find the exact value of sine of 45 degrees. Draw a reference triangle. We would end up with square root 2 over 2. But what about if we want to find the sine of 75 or some other combination? So is it the same as the sine of 30 plus the sine of 45? In other words, could I factor out sine? In essence, that's what I've done. I've factored out sine and I'm adding the two numbers. Well, an easy way to check this is to use a calculator and compare the approximate values. So here's my calculator. I'm going to check the mode. And I'm working in degrees, although the things we're learning today, they could be done with radians or degrees, it doesn't matter. But I'm just going to work with degrees, so let's change that mode. And then let's find the sine of 75 degrees, the approximate value there. And then let's find the sine of 30, close those parentheses, plus the sine of 45. Okay. We can see that these are not equivalent, so you can't just factor out or distribute a sine function. So I have to say a big no to that. So this should remind us of other operations that we can't necessarily distribute. For example, the square root of 75 is not equal to the square root of 30 plus the square root of 45, so you can't just distribute a square root. The log of 75 is not equal to the log of 30 plus the log of 45. So we've seen things like this before where you can't just distribute whatever function you're working with. Okay, so we've talked a lot about what we can't do. What can we do? Turns out that there are identities that tell you how to combine things to get the sine of 75 or other angles that we can talk about later. They're called sum and difference identities. And if we had a whole class period, I would prove these for you, so you wouldn't feel like they were just coming out of the blue, pulling them out of thin air. But we're not going to take the time to prove these today. So what I'm going to do is just tell you what the identities look like and then show you an example of how to use them. So I'm going to start with the sum and difference identities for the sine function. So if you have the sine of a sum of two angles, I'm going to say those angles are alpha and beta. So we have the sine of alpha plus beta. We can find that by finding the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So that's the angle addition identity for sine. That's the sum identity for sine. Let me show you an example. Let's go ahead and do the sine of 75, the one I was talking about earlier. So we know that 75 is the same as 30 plus 45. Now it's also the same as 20 plus 55 and 1 plus 74, etc. There's lots of combinations, but we want to choose two numbers that we do know how to find exact values for. That's why I chose 30 and 45, and it doesn't matter what order I put them in. So then, according to the identity, alpha, our first angle, will be 30. And beta, our second angle, will be 45. So the first thing we're going to do is sine alpha, so sine 30, times cosine beta, cosine 45. I'm not going to write the degree symbol every time. Hopefully that's okay, just being lazy. Plus cosine alpha is cosine 30, times sine beta would be sine 45. Now you know how to find each of those values: 30 degrees, reference triangle, and 45 degrees, reference triangle. Sine of 30 is 1/2. Cosine of 45 is square root 2 over 2. Cosine of 30 is square root 3 over 2. Sine of 45 is square root 2 over 2. Simplify by multiplying these first two fractions, we get square root 2 over 4. And multiplying these last two fractions, we get square root 6 over 4. And you could leave your answer like that. I'm perfectly fine with that. Or if you want to combine them into a single fraction, it's square root 2 plus square root 6 over 4. Just remember that you can't add square root 2 and square root 6. It's not like you get square root 8. Now let's just grab the calculator again. So let's calculate square root 2 plus square root 6 divided by 4. You see the value we got for sine of 75 is the same as that value, so that's a nice check. Okay, let's move on to another identity, and the next one is the difference identity for sine. So this is if you had sine of alpha minus beta, a difference of two angles. And this is the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. Notice it's just like the first one, except it has a minus instead of a plus. So this is the angle subtraction or difference identity for sine. So let's do an example. Let's say we wanted to find the sine of 15 degrees. So what two angles can you subtract to get 15 degrees? It could be 45 minus 30. It could be 60 minus 45. It could be 330 minus 315. The point I want to make is there are lots of different combinations that you could use that subtract to give you 15 degrees. Always choose two angles that are angles that you know how to find exact values for, like 330, 315, 60, 45, 30, etc. I didn't list all the possibilities. There are lots and lots and lots. And it will give you the same answer every time if you do it right. So I'm just going to do the first one, because why not? It's the easiest one. Sine of 45 minus 30. So according to the identity, 45 is my alpha, 30 is my beta. I'm going to have sine alpha, sine 45, times cosine beta, cosine 30, minus cosine alpha, cosine 45, times sine of beta, sine 30. And then, again, using those reference triangles and finding those exact values, we substitute those in and simplify, and the answer is square root 6 over 4 minus square root 2 over 4, or if you prefer, you can write it as square root 6 minus square root 2 over 4. And let's just do a check with the calculator. Sine of 15 degrees, there's the approximate value, and then square root 6 minus square root 2 divided by 4. See the same approximate value. So the point of using the identity is so that we can get an exact value and we don't have to use the approximate value. Okay, next I'm going to show you the angle sum and difference identities for cosine. Cosine of the sum of two angles. Cosine of alpha plus beta is cosine alpha times cosine beta minus sine alpha sine beta. And cosine of the difference of two angles, cosine of alpha minus beta, is cosine alpha times cosine beta plus sine alpha times sine beta. So notice that those are very similar to one another. The only difference is the sign change in the middle. And the different thing comparing this one to the last two we looked at is that when you have a plus for cosine, you're adding two angles, you actually have a minus in the identity, and vice versa. Okay? So let's go ahead and look at a couple of examples. Okay, let's find the exact value of cosine of 105 degrees. Now you ask yourself, what two angles could I add together, or what two angles could I subtract to give me 105? And these need to be angles that you know how to find exact values for. So you have lots of choices. One choice would be 60 plus 45. Another choice would be 150 minus 45. And you have other choices as well. Just decide what you want to use and stick with it. So because I did 60 plus 45, it's a sum with a plus, so I'm going to use the top identity, cosine of alpha plus beta. And that gives me cosine alpha, which is cosine 60, times cosine beta, which is cosine 45, minus sine alpha, which is sine 60, times sine beta, which is sine 45. Okay, then you draw your reference triangles and you find all those values. We get 1/2 times square root 2 over 2 minus square root 3 over 2 times square root 2 over 2. Now I just caution you when you're picking your angles like 60 and 45, if you happen to pick something that's not in the first quadrant, you might have some negative exact values, so don't forget about those. For example, in here instead of 1/2 maybe you have negative 1/2, or in here instead of square root 3 over 2 maybe you have negative square root 3 over 2, just depending on which angles you chose and which quadrants they're located in. So this answer is square root 2 over 4 minus square root 6 over 4, or you can combine those if you want. And then, of course, you can use the calculator to check and see that cosine of 105 really is equal to that value. Okay, let's do one more example, and this example is going to be a little bit different style. So this one says that the tangent of alpha is 3/4, and alpha is in quadrant 3. And it says the cosecant of beta is square root 5. And beta is in quadrant 2. So basically we're getting all these clues about alpha and beta. And the goal for this problem is to find the cosine of alpha minus beta. Okay, so according to our identity, to find the cosine of alpha minus beta, we have to find the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. So we have 4 different values to find. And the way we find those values is by drawing a reference triangle for alpha and by drawing a reference triangle for beta. So remember, tangent of alpha is 3/4 and alpha is in quadrant 3. So let's draw that. That means the terminal side is in quadrant 3. So there's our reference triangle. Alpha is technically all of this, all the way around from the positive x-axis to the terminal side. And 3/4 means we should put a -3 on the opposite and a -4 on the adjacent. Use the Pythagorean theorem and you get 5 for the hypotenuse. So once you have all the sides of the triangle labeled, you're ready for its exact values. And let's do the same kind of thing for beta. So we're told that beta is in quadrant 2. That means the terminal side is in quadrant 2. So there's the reference triangle, and beta is this entire angle here. And if we're told that the cosecant is square root 5, we can turn that into a fraction by making it square root 5 over 1. And cosecant is hypotenuse over opposite. So let's put the square root 5 on the hypotenuse and the 1 on the opposite. Then we're going to use the Pythagorean theorem, and we end up with 2 for the adjacent. And you need to put a negative on there because we're going left. Okay, so now that we have our reference triangles, let's go back to our identity and find the cosine of alpha. Using this triangle here, it's -4/5. Find the cosine of beta. Using this triangle here, it's -2 over square root 5. Find the sine of alpha. Using this triangle here, it's -3/5. And the sine of beta, using this triangle here, it's 1 over square root 5. So we're going to simplify this answer, and we have 8 over 5 square root 5, whoops, that should be a 5, minus 3 over 5 square root 5. We can go ahead, since they have the same denominator, and subtract the numerators. We have 5 over 5 square root 5. It's not always going to work out so nicely with the same numbers like 5 everywhere. If we cancel the 5 on the top and the bottom, we have 1 over square root 5. And then if we rationalize, our answer is square root 5 over 5. Okay, So even though we don't know the measure of alpha and we don't know the measure of beta, we were able to use the clues to find the answer to the question. Now before we go, I'll just tell you, we're not actually going to practice them, but I'll just tell you that we also have angle sum and difference identities for tangent. Tangent of alpha plus beta. What you can do to derive it is you take, remember that tangent equals sine over cosine, you take the sine identity divided by the cosine identity, do a whole bunch of algebraic gymnastics, and bada boom bada bing, you get this. Tangent alpha plus beta equals tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Because this one is a quotient, the simplifying can get rather tricky. Gives you a chance to practice lots of different algebraic skills. Tangent alpha minus beta is very similar. Tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. So the signs are different. Other than that, these two look alike. Okay, for your assignment, I've made you a worksheet, and what you're going to do on the worksheet is first write down all of your basic 8 fundamental identities, and then you are going to do 4 problems that are just like the 4 examples I worked through in this video. So you'll be able to kind of look back at the examples if you need to. Thanks, everybody.